we mentioned that the synchronous sequential circuits that contain clocks must have memory elements, or what we call flip-flops. In this part, we will look at the latches, and the latches are needed in order to implement flip-flops. What is a latch? Well, first we define the flip-flop as a circuit that maintains a binary state, which means if that is a flip-flop, if we store one, it will maintain the value of 1. And if we save 0, it will maintain the value of 0. So that's what a storage element means. And there are different types of flip-flops that we will look at later. The basic type of flip-flops are called latches. This is what we study in this part of the course. Latches are basic circuits from which all types of flip-flops are constructed. That's why it's necessary to understand the latches in order to be able to understand the flip-flops. Latches are used more in asynchronous sequential circuits, which we don't really discuss in this course. We only discuss the synchronous, but we need to understand the latches. First, we look at the SR latch, and S stands for set and R stands for reset. SR latch can be constructed in two ways, either as two NOR gates connected back to back, we call them cross-coupled, or two NAND gates again connected back to back or cross-coupled. Cross-coupled means the output of one gate is given as the input of the other gate and vice versa here. Same thing for the NAND gate latches. This output is the input to this gate and this output is the input to the other gate. Notice that the set here in the NOR gates corresponds to Q prime, while the reset corresponds to Q, whereas the set here has a Q on this gate and the reset has a Q prime on this gate, and these we will derive soon. The SR latch then, in order to summarize, is a circuit with two cross-coupled NOR gates or two cross-coupled NAND gates, as will be explained next. We start with the SR latch with NOR gates first. And this type of latch has two useful states. Why do we say useful? Because there are some states that are not useful and we want to avoid them. The two useful states, the first state is called set state, and set state is the state when the output Q is equal to 1 and the Q prime is equal to 0. And the second one is the reset state, which is when the output Q is equal to 0 and the Q prime is equal to 1. And these are the two states that are used to store the 1-bit information in the latch. So we store 1 or 0 by making the latch set or reset respectively. The output Q and the Q prime are normally, not always, normally complement of each other. We say normally because there is an abnormal situation that we want to avoid. It is called an undefined state or unwanted state, or a state that we want to avoid. And this state when both Q equal to 0 and Q prime is equal to 0, and it occurs when both inputs R and S are equal to 1 at the same time. Look at this very simple circuit. If R is 1 and S is 1, what will happen? This is an OR gate. Irrespective of what is this must be 0. And this must be 0. And this is the state that is undefined and we want to avoid by all means. So the SR latch with NOR gates, under normal conditions, both inputs of the latch R and S remain at 0 unless the state has to be changed. And to lift the latch in the set state, S must be 1, and to set the latch in the reset state, R must be 1. So it's very simple. If we want to set the latch, we make S is 1, and if we want to reset the latch, R is equal to 1. The inputs S and R must go back to 0 before any other change to avoid the occurrence of the undefined state that we have just introduced earlier. The latch goes to the set state or reset state and stays there, even if both inputs return to 0. So let us analyze this latch again here on this diagram. Let us take the situation first where R is 0 and S is 0. What will happen? This is a Q prime here, and this is a Q or 0, Q, inverted Q prime, and the Q prime or 0 is Q prime, inverted Q, and that's what we say that the latch maintains its states. Now, let us make S is equal to 1. So we make this 1. And R remains 0. When this is 1, irrespective of what is a Q, this must be 0. Because 1 or Q is 1, inverted 0. And when this is 0, this must become 1. So when S is equal to 1 and R is equal to 0, Q is 1 and Q prime is 0. And we say that the latch is set now. Let us take S back to 0. What will happen? If S remains to 0 here, this one actually came here. So 1 or 0, 1, inverted 0, 0, 1. So the latch maintains its states. It keeps Q equal to 1 and Q prime equal to 0, although both R and S are 0. Now, let us take the other way. Let us start from 0, 0 again. This is 0, 0. And make R equal to 1. So if this is 1 here, or Q prime inverted, this will be 0 here. So this is 0. And this is 0 here. And this will be 1. So when R is set to 1, Q prime is 1 and Q is 0. And we represent this with this row of the function table. R is 1 and S is 0. Q is 0 and Q prime is 1. Now let's make R again 0. What will happen? When R is 0, this one here that came from Q prime will keep this 0 and this 1. And the latch will keep Q equal to 0 and the Q prime equal to 1, although both R and S are zeros. And of course, as we mentioned earlier, if both are 1s, the outputs will be zeros, which is the forbidden state. What we would like you really to remember from this slide here is that when R and S are both zeros, the latch can store either 1 at a Q or 0 at a Q, depending upon which was 1 earlier. S is equal to 1 will keep Q 1, and R is equal to 1 will keep Q 0. So, to summarize, when both inputs S and R are equal to 0, the latch can be in either the set state or the reset state, depending on which input was more recently a 1. Same thing actually with the latch with NAND gates, exactly same way of analysis we followed here. It has also two useful states: the set state when Q is equal to 1, and of course Q prime is equal to 0, and the reset state when Q equal to 0 and the Q prime is equal to 1. Also, Q and Q prime are normally the complement of each other. And there's also an undefined state that we want to avoid, which is when Q is equal to 1 and the Q prime is equal to 1, and it occurs when both inputs are equal to 0. So if this is 0 here and this is 0, it doesn't matter what is a Q prime and what is a Q, this will become 1 and this will become 1, and this is the undefined or undesirable state that we would like to avoid. This latch is very similar to the previous one actually, which is under normal conditions, both inputs of the latch R and S remain at 1 unless the state has to be changed. And to let the latch in the set state, S must be 0. To let it in the reset state, R must be 0. And the inputs S and R must go back to 1 before any other change. Why? In order to avoid the occurrence of the undefined state. And the latch goes to the set state or the reset state and stays there even after both inputs return to 1. We will show this again with the following circuit, the function table. So this is a latch. As we said, usually we keep R is 1 and S is 1. So S and R are both 1s. And if this is 1, this is a Q, and this is Q prime, and the Q prime and 1 inverted will be Q, Q and 1 inverted Q prime. So the latch is stable. Whatever Q is, it is maintained. Now, to make the latch in the reset state, we make R equal to 0. If R is equal to 0, this will be 1. And if this is 1 and 1 inverted 0, this will be 0. And this is the first row in the function table, which is R is equal to 0, S is 1, Q 0, and the Q prime is 1. Now, this one here will be here. And if R goes back to 1, this 0 here will be here. 0 and 1 inverted 1. And this one, it will be 0. So the latch will maintain the 0 state after S and R go to 1. In order to set this latch to 1, we make S is equal to 0. So if this is 0, this will be 1 immediately. And if this is 1 here and 1, this will be 0, which is this row in the function table, which is when S is equal to 0, Q is equal to 1. Again, if we make S back to 1, if we make this back to 1, the latch will keep its state of 1 here. Again, as we mentioned earlier, if both are zeros as inputs, the outputs will be both 1, and this will be the forbidden state. Now, remember that when both inputs S and R are equal to 1, the latch can be in either the set state or the reset state, depending upon which input was most recently a 0. And that's why we see here both are 1s. We see Q is 0, and both are 1s, Q is equal to 1. That's exactly. And because the NAND latch requires a 0 signal to change its state, it is sometimes referred to as an S prime R prime latch. So instead of SR latch, usually we say S prime R prime or S bar R bar latch, same thing exactly.